After this really nice talk given by my colleague Florian, I will go more on some of the other research lines that we are doing in the group, more related towards the application side for chemistry of machine learning force field. So the thing is that I'm a chemist, and we have been seeing all these days that machine learning force fields still need to be improved. We need to make better the physics, we need to have better data sets, we need to have better levels of theory. But now, one of the main ideas is, okay, once we have these machine learning force fields, now how come we can make them lightweight enough and fast enough that we can actually try to model wet chemistry on, let's say, consumer-grade architectures, like a laptop. So with this kind of idea to trying to democratize chemical physics, we started this research line, the so-called MARS project, which actually has three main additional parallel research lines. MARS, which was already introduced yesterday in the hands-on session, which is devoted to conformational sampling and essentially the exploration of molecular energy landscapes, mainly done by Sergio, who unfortunately is not here. And then we have both MARS rover devoted to chemical reactivity and MARS MS for mass spectra. So I will try to go through a bit of what we are doing in those different research lines and what applications we are trying to achieve. And in the near future, trying to model all this with chemistry on a laptop. So one thing that I would like to mention before starting is that all of these initiatives are based on the fact that we will have model agnostic packages. So all of the results that you will see here will be some with solar, but these packages can be run with any force field of your choice, provided that they provide the right access to the observables that we want. That's the first thing. And the other thing is that as we want to, let's say, democratize science, all the results that you will see in these slides have been performed on essentially portable GPU that we can have on a laptop. So let's start with the MARS project. So in MARS, as we already introduced yesterday, we are essentially, which stands for Machine Learned Force Field for Automated Conformational Relaxation and Sampling. We are trying to tackle the problem of the exploration of the molecular energy landscape. And with this, Sergio tried to tackle four main tasks. First of all, we tried to address the problem of conformational sampling. So essentially trying to map the points in the potential energy surface where we have the various potential wells. For that, I will not go into the algorithmics because this would take quite a lot of time, but in a nutshell, starting from an XYZ structure, what we do is to essentially create an initial bond topology, which is done on the fly, and then we run a collection of parallel MTD metadynamic grids. This results in a collection of structures that are then filtered based on both energies and structures with RMSD, and this allows us to have a window of potential wells that we have in the conformational landscape of these molecules. For instance, here you can see an example run with solar on a laptop of a rotaxane molecule spanning within a 10 kcal per mole window. So this gives us the potential wells, but then we need to characterize them, right? So for this, we can do infrared spectra. Well, there are many ways of doing this, but currently in MARS, there are like two built-in utilities. We can, as it was already mentioned by Tobias and by Florian, we can actually use, for instance, analytical Hessians, and we can try to go a bit beyond trying to do MD simulations to try to capture anharmonicity effects. For instance, the output that you would get is something like this, which you would get the corresponding IR spectra, provided that the machine learning force field that we are using has access to the dipole response of the system. Otherwise, we will not be able to get the intensities. Not only that, but the code is able to do automatic characterization of each of the vibrational peaks with an embedded functional group library of around 250 common chemical motifs, mostly oriented towards organic chemistry and biomolecular chemistry. So with this, we have the potential wells and we have the characterization of them. But one of the topics that has been addressed in this, and concerns, I would say, that has been addressed in this conference is the need for solvation, because solvation plays a huge role in reshaping this energy landscape. So, of course, we need to work in implicit solvation models, but this is kind of challenging, as we already saw. So, in the meantime, if we have a machine learning force field that is lightweight enough, we can just do explicit solvation. So, for this, MARS rover has a microsolvation protocol, which was quite cleverly developed by Sergio. It actually can do it in two different ways. We can build the solvent by a collection of Fibonacci spheres that are progressively larger in the space, which is called the layer solvation approach, which generally leads to a slightly more unpacked structures, or we can apply a varostat, which is the second approach that is here, and this results in the most intimate solvent cell that you can have around one of these molecules. But not only that, once we have this, we can already also apply an isotopic potential in the space, in line with, for instance, what is done in packets like CREST, and we can actually do non-covalent interaction sampling. For instance, here you can see a simulation of the benzene dimer with solar, which will ring a bell to any chemist in the audience, where we can see a pi-pi stacking alternating to a T-shaped structure. So let me show you an application of what can we do with this, again on a laptop, trying to tackle the problem of chemistry. And for this, we decided to focus on this particular paper, which to me is particularly nice, which tries to tackle the problem of host-guest chemistry. So the idea is we can have two molecules, in this particular case, proline and beta-cyclodextrin, which can recognize each other. And as you can see, these molecules have a lot of flexibility, especially the beta-cyclodextrin, which is a highly fluxional skeleton. So in itself, doing the conformation landscape for those is actually quite challenging. But of course, when we put them together, this results in an even higher diversity, and you can see that the proline is interacting quite predominantly with the polar groups of the beta-cyclodextrin ring. In fact, in most of the structures, you would see something like this, where the proline is trying to interact through a tightly packed hydrogen bond network in the system. So now the idea is that, as Florian already explained, these vibrational probes respond to the local electric field. So the idea is, okay, what happens now if we check the amine scissoring of the proline in the presence of the beta-cyclodextrin? And as you can see here, there is a prominent change in the response, which allows us to model the experimental results with quite large accuracy. So we are actually able to model these kind of experimental observables, providing, let's say, a proof of this kind of host-guest complexation phenomenon. Let me now move to the second research line of the Mars initiative, which is devoted to chemical reactivity. And I would like to mention that as a chemist, in most of the field of chemical reactivity, it used to be considered that the problem was, when studying computational aid chemical reactivity, it used to be thought that the problem was essentially to have access to fast energy and force evaluations. But now with machine learning force fields, this is not true anymore. I mean, we can have access, and we have seen this, to really fast evaluations and really accurate evaluations of energies and forces. So then you might think that chemical reactivity is already solved. The answer is that not really. And the problem is that chemical reactivity, as other parts of chemistry, has a lot of human guidance. And this is, first of all, this is problematic for us because this limits the rate of discovery of reactions, but this is also really dangerous because it also introduces biases, human biases. So trying to solve this problem, we introduced the Mars rover initiative, which essentially tries to tackle autonomously chemical reactivity with machine learning force fields. Mars rover is essentially based on four fundamental pillars. First of all, and I would say is the most important one, we do not have any sort of prior reaction mechanism, meaning that we only need the endpoints, so the starting and the final structures. More importantly, it's, as I've told you, model agnostic, so we have a collection of embedded machine learning phosphates, including MAZE, UMA, and Solar, but you can also use your very own custom calculator. It also allows for fully automated protocols, and more importantly, it accounts for multi-step reaction discovery, meaning that we can actually discover hidden intermediates in the reactions. Let me show you how this works with an example. Let's imagine that we want to study this kind of Claisen-like rearrangement reaction. For the chemistry audience, you'll notice that this is not exactly a Claisen-like reaction. It's the transformation of orthocresol to anisole. So, given this transformation, the only thing that we need is the input structures. Given the reactant and the product, the first thing that Mars rover will do will be to optimize it to the level of theory provided by the machine learning phosphate. Then it will try to connect, build a collection of intermediate frames through different protocols, including the NEB method, not Natchez Big Bang, and this will result in a collection of possible transition state guesses. Then it applies a refinement of these transition states to the desired convergence, and finally, it accounts for reaction coordinate validation. So it will actually check that this transition state is connecting the two potential wells of the surface. Let me show you what's the output with this particular example. So what MassRover gives us is the full reaction history. So now the question is, how many steps do you think we will have in this relatively simple transformation? Bear in mind that we are essentially just flipping a methyl group from one carbon atom to a nearby one. You may think that this is like 1 or 2. Well, let's see what MassRover in combination with Solar V1 has to say. As you can see, this process is actually a multi-step reaction discovery that entails multiple steps. First of all, MassRover Solar considers that we need to rotate the methoxy group. This is followed by a methyl transfer that loses the aromaticity of the scaffold, and this is then followed by a proton shuttle that recovers the aromaticity, and with a final rotation, we will obtain the final product. All of this is done fully automatically without our intervention. We only provide the reactant and the product. So now the thing is how well this is actually performing. In a set of 20 elementary reactions spanning across different chemical spaces and across different charge states, we get really good transition state geometries. Actually, you see an RMSD of around 0.30. In reality, it's slower, it's around 0.1 angstroms for Solar V1. And more importantly, we get activation barriers out of the box with a mean absolute error of around 7%. This may seem large, but bear in mind that we are using, in this particular case, Solar V1 out of the box, which has not been specifically trained for chemical reactivity. So it's one of the essentially manifestations of general purpose machine learning enforcements. And more importantly, we are really fast. So we are at least anywhere between 100 to 1,000 times faster running the code on a laptop as opposed to running it on an HPC cluster with 48 cores with quantum chemical packages. In fact, you can see in this figure kind of a scaling law of 3 different DFT functionals. On top, you will see B3, PB0, and Omega B97 running on an HPC with 48 cores as the number of atoms in the reaction increases. And on the bottom line in blue, we have MassRover in combination with Solar on a laptop. So we are typically taking about 1 minute. For reference, you also have XTB, again on 48 cores, and we are just as fast as STB, and we are considerably faster when the number of atoms increases. For instance, we have run up to 600 atoms on this laptop. Okay, so this clearly proves that works, but we really need to push a bit the limits, right? So for this, we decided to set up a collection of challenges with only 3 constraints. First of all, we will stick to the Solar machine learning force field, V1. Why? Well, because it's lightweight enough that we can actually run it on a laptop, and that's what actually we want if we want to screen a large collection of chemical spaces. Not only that, but we will allow for different charge states, but only a singlet spin multiplicity, and everything will be run on a laptop. With this, we came up with a total of 110 different chemical challenges, and unfortunately, I cannot go through all of them, but I will like you to give, let's say, 2 case explanation example that is probably one of my favorite ones. So let's start with proline-catalyzed aldol reaction. This reaction is a chemical transformation that entails the coupling of 2 carbonyl compounds to produce a 1,3-hydroxycarbonyl derivative. The really nice thing about this reaction is that it can be catalyzed by the presence of an organic molecule, proline. And it's not only that, but if proline is an antipure, so if we start with the S or the R forms of proline, then this can act as a chiral print, imposing chirality on the final product. So we can obtain an anti-selective reactions. Being a catalytic cycle, as you can imagine, this entails a lot of reaction steps, and this is what is proposed in the literature. And this is what we get out of the box with MassRover Solar V1. So we get not only the right reaction steps, but actually we get the right qualitative trends in the reaction energy profile. In fact, as you can see here, the very first 3 steps are considered to be common to both paths, regardless on whether the reaction takes place to the bottom or the top parts of the scaffold. And then we see a splitting of the potential energy surface, depending on whether the reaction takes place to the Re or the C phase. Not only do we get the qualitative splitting, but actually we can predict the enantiomeric excess, which points to around 90%, in line with the experiment of around 76%. Everything, again, running on a laptop with a 4 gigabytes GPU. Okay, but what about solvent effects? We have seen that solvation is actually really important, and it's also the case for chemical reactions. For that, we can now have access to fully explicit solvated reactions. For instance, in this case, we decided to study a reaction that is well known to be quite sensitive to solvent effects and self-substitution, nuclear substitution reaction, SN2 reaction. In the presence of water, you can see that not only do we get the right trend in the energy change, but also you see that we have quite a large energy penalty, which is directly attributed to the reorganization of the hydrogen bond network around the water scaffold. So we are actually able to even recover this kind of solvent trends in these systems. Just for reference, and as I told you before, this we have running with different solvents, spanning across different polarities, and we have been able to run it up to 600 solvation atoms. Okay, let me just briefly go to the very last part of this talk, which is word. Okay, only 4 minutes. Which is devoted to mass spectroscopy. And why? Because we thought, okay, if chemical reactions work, then in principle we should be able to predict how molecules may fragment. And this is directly related to mass spectroscopy. All of you probably have heard about this technique, but in a nutshell, we just need to ionize the sample. Then we essentially accelerate the ions, and then in the presence of a magnetic field, this results in a deflection of the path, and then they hit the collider. If we actually want to predict this fragmentation pattern, we really need to predict the ionization part. And for that, I don't have time really to go into detail on how we can do it, but we came up with the following protocol. So in a nutshell, what we are doing is to force the system to get ionized with, in this case, simple protonation. So we look for the different protomers of the molecule, and then we look for the ones that are more stable within a protonation and energy window. Then we perform a simple relaxation to check if they are long-lived enough, and if so, then we need to deposit energy into the system. Trying to be as close as possible to the experiment, we have two different ways of depositing energy. So we can do it a collision-induced energy deposition, where we shoot different particles like argon or nitrogen into the system. This is a real simulation, by the way, with SO3LR, and the kinetic energy is translated into the vibrational modes, which eventually results in the breaking of the system. Not only that, but we can just simply rank up the temperature of the MD, and then this will result in the fragmentation of the system. What's the output? So what we get is a fragment-resolved mass spectra. In this case, you get the mass spectra, for instance, for acetamide, and just for reference, you have the experimental values. The intensities are still hard to get because, of course, this depends a lot on the experimental setup and the derivatization technique that has been employed for the preparation of the sample. So it's not quite clear how to tackle that. But now let me just show you how this works in a collection of 12 differently drug-like molecules randomly sampled from the MONA mass spectral database. And in this figure, you see on the top is like a kind of a party plot, which on the top you see the mass spectral computed with solar V1, and at the bottom you see the experimental value. So we get really good accuracy of the position peaks, which is in line with state-of-the-art performance. And how fast are we? Well, the answer is that this depends actually a lot on the size of the system and the kind of technique that we use, the number of trajectories, and also the way to deposit energy, but we are roughly between 10 and 30 minutes on a laptop for up to 50 atom molecules. So with this, I would like to conclude by highlighting that, as Florian said, protonation equilibria can be accessed with enhanced sampling techniques. Also, the properties of solvents and solvatochromic effects can actually be studied, although they are quite challenging, as he mentioned, with machine learning force fields. And for this, we need to tackle better and more complex physics, including nuclear quantum effects. And also that we are starting this Mars Initiative project to try to deploy these machine learning force fields that are lightweight enough to try to model chemical physics as close as possible. With this, I would like to acknowledge all the funding agencies for financial support, and of course the Theoretical Chemical Physics Group of Alex Tachenko, and all of you for your attention. Thanks a lot.
We have enough time for questions. Who wants to start? So we have one question online. Yeah. So Amir Madizardoshti is asking, could you explain how you generated the initial training data set for the aldol reaction, and I guess for any reactions?
We don't have any training data. This is just it's directly out of the box solar. So we don't do any fine tuning or pre-training. It's just the original model.
Can you explain why it works?
Well, actually, that's a bit more challenging because theoretically, although solar has seen some, let's say, broken bonds in QM7X, it's not that clear how it can actually perform that well in chemical reactivity. My best guess is that in reality, when you do chemical reactions, you are not breaking all of these bonds, you're just altering part of the near equilibrium surface, and this is just good enough to do reactions. Also, the treatment of long-range the long-range interactions and the physics embedded within the model, I think that they help particularly with the, for instance, repulsion in the short tail. And
Any question? I have a curiosity. Do you compare, this conformational stuff that you are doing? Many of us have used CREST for generated conformers. Do you have like a benchmark, like an efficiency benchmark, comparing the method with CREST?
Yeah, we do in the low number of the low, small to medium-sized molecules, we are just about as fast as CREST. In the large molecular size, we are considerably faster.
Oh, okay. But what about the conformers? So you
the conformers, in fact, there are some conformers that cannot be recovered with XTD. We do recover, although that depends, of course, this is model agnostic, so it depends on the machine learning perspective that you ask. So Maze, Solar, Yuma, they have different performance, so it's really different.
Okay, interesting. Someone else? Questions?
As we were also already talking about CREST and XTD, so the Grimmel group also has a mass spectra code, QC XMS. So the initial version also sounded similar to yours, where you were using NMP calculations to fracture the molecule. Well, I think their second version goes through calculating activation barriers, like the thing you showed earlier in the talk. Can you comment on which one do you think is the best way to figure out the fragmentation?
The good thing is that if you actually do it with, we plan to kind of couple mass rover with Mars mass so that you can actually do it. The really good thing of doing it with activation barriers is that you can actually account for the probability of that fragmentation to take place, because otherwise, for instance, when you deposit energy, the thing is that if you do it, for instance, with a collision-induced activation, then you really need to sample all probabilities of depositing energy by multiple collisions, because currently what we are doing is just shooting, for instance, an argon particle towards it. In reality, the energy deposition is thought to be considerably cumulative, so you would need a probability and a distribution of projectiles at different speeds, at different temperatures, and this will be considerably more expensive because you would need to run more trajectories. So probably the time that you spend running the fast barriers is considerably more efficient, because then once you have all that data, you can actually account for the probability that the fragmentation will actually take place. But this is really a work in progress, so we need to check on that.
Any question? No?
We have one question online from Aidar Alimbayev. What kind of the model do you use for Mars MS?
All the results that I saw here is Solar V1.
Okay, well, no more questions. Thank you, Miguel.